So we define the two functions, right? So the mu function and the phi function. So in this theorem, we'll see relation between the two of them. So how
Phi
these two?
phi equal to minus 1 power k. Yeah.
No, that is mu. Mu
That's
is
in
that.
the yeah.
Yes, yes.
And phi equal to summary of divisor
Right.
of 1. GCD 1. Yeah.
Right. So number of so phi of n counts the number of numbers that is coprime to n and less than n. Right. So that is the phi of n.
Mm.
Right. So yes. So proof will let us see the proof. So phi of n we can write like this. So this is also summation k equals to 1 to n. So this way, this thing. So this is the greatest integer function, right? This box of x.
Mm.
So this is the greatest integer function, right? So here I can write it as summation of this thing because suppose the GCD of n and k, so that is not equals to 1, right? If the GCD is not equals to 1, in other words, if the GCD of n and k is strictly greater than 1, then 1 by nk, the GCD of nk will be strictly less than 1, right?
Mm.
So then the box of that will be 0, right?
Mm.
I take box of that, so that will be 0, right?
Mm.
So if I take the summation over all n from my k equals to 1 to n, the 1 over GCD of n comma k. So this term will only survive when the GCD is 1, right?
Mm.
So that's why I can write like this, right?
Mm. Mm. Yeah. Yeah. Mm.
Right. Okay. So now if I use this theorem, so if let me go to the back, we proved this one. So mu of d, right? So mu, I think we defined here, right? Yes. Now we'll use this theorem.
Mm.
So 1 over n, this box of 1 over n. So that is nothing but the summation over all d divides n mu d, right? This we prove,
Mm. Yeah.
right? So we'll use that. So here we'll replace this box of. So what I know that mu of d summation over d divides n. So that is nothing but box of 1 by n, right? So that is from the theorem.
Mm.
So here what I can replace. So here instead of so d divides n mu of d. So here n will get replaced by n comma k, the GCD of n comma k. So that is 1 by n comma k, right? So by replacing this n by the GCD of n comma k. So this is the application of that theorem, right? So this I can replace. Okay,
Mm.
right. So then what is our summation become? So phi of n, after replacing this thing, it becomes summation k equals to 1 to n. Then summation d divides GCD of n comma k mu of d, right?
Mm.
Right,
Mm. Mm. Mm.
right. So now okay, this I can rewrite this summation as like this. So k equals to 1 to n. So d divides GCD of n comma k implies d divides n and d divides k, right? Mu of d. So I can write like this.
Mm.
So for a fixed divisor D, so for a fixed divisor D of n, we must sum over all the k. So we must sum over all those k in the range 1 to n, which are multiples of D,
Mm.
right? So that is what we are doing, right? So if I choose a fixed, suppose I choose a fixed divisor D, that is D divides n, then we sum over all those k such that that are multiple of D, right? Because I have these two conditions, right? D divides n, D also divides k, and k is running from 1 to n.
Mm. That your way.
Yes, see it once.
Mm. 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 That's the meal. Oh, yeah.
Yes,
So, meal, uh, meal D N K. In submission,
yes,
in submission, the divisor creature of D N K about replacing by N K.
yes, yes. So here, this is the result from the theorem, right?
Yeah.
But here in the summation I have box of 1 by n k, right? So I replace n by that quantity because I want to replace this whole thing by one summation.
Mm. But how we can reply N by GCD of NK?
Yes, yes. So here it is. So this is true for any value of n, right?
Ah.
So this theorem is true for any value of n. So if n is any integer, then 1 by n, that box, I can write it as summation of this quantity, right?
Mm. 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 Reply by NK. Ah.
Right. GCD of n and k.
NK. Uh,
Yes, so GCD of nk is just another integer, right? I'm just replacing it because it works for any n.
just replacing, not
Yes, yes,
okay, okay. That's mean from N to K or N to M. Just that is
yes,
right.
yes, yes, yes,
Okay, okay. Okay. So phi equal to summation K equal to 1 to N.
yes,
Okay, 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 okay. We want to use.
yes. We replace this quantity by this
Mm,
summation. So this
okay,
summation comes,
okay.
right?
Mm, mm, mm.
Now d divides the GCD of nk means imply d divides n as well as d divides k, right?
Mm, mm,
Okay. So now we have a double summation. So we have to so we have a double summation, but the proof is I have to bring into a single summation, right?
mm,
So now that we have to think how to bring it into a single summation. So let us see. So if I fix any divisor of n, right? Then
mm,
in this total summation, what are counting? We are counting those k in this range 1 to n, which are also multiple of d, right? Because d divides k.
divide to K. We fit N, DN.
Right,
We fit DN. So remaining is DK. Ah,
right.
for on K. For on K.
Okay.
Yeah, yeah. Sum must sum over on the k in range.
right? So uh, so if we write k equals to some, so if we write k equals to some q times d, because k divides because d divides k, so then 1 less than equals to k less than equals to n. This if and only if for some the q lies between n by d, right? So here d divides k, so I can write k as some q times d, right? So since it is k is varying from 1 to n, so this will only hold for some q that is lies between 1 and n by d, right?
Mm. Mm.
Right. So what I can do is, so this summation, this phi of n. So from the previous line, what I have, so I have k equals to 1 to n summation d divides n and t divides k mu of d. So this I can change the my summation and write down like this. I interchange the summation d divides n, and I take over all the q's, q equals to 1 to n by d mu of d,
Mm.
because we are taking all the factors of all the multiples of d up to k, so up to n by d.
Wait, consider a little bit.
Yes,
Uh,
yes,
yeah,
yes. This step is
k equal to qd.
right.
Yeah, that's right.
Hmm.
qd, qd. So q from yeah, is the okay.
Right.
Q from that's okay. We remove dk. Yeah, that's mean we just you we just you hmm? q equal to one.
Right. So q equals to
In
1
the
to up to n by d. That is the maximum q we can have, right?
in the
Yes.
hmm? But here qd submission of the n that's okay.
Yes.
Hmm? Here q equal to one.
Yes.
Q equal to one.
Yes. So first of all, let us understand this double summation. So first, for any k is running from 1 to n, right?
Uh,
And then we are taking a divisor d that divides the GCD of n comma k, right?
uh,
Okay. So what we are doing is we are breaking that term. So suppose this summation is over d divides n as well as d divides k, right?
mm,
So if d divides k, I can so this k is running from 1 to n. I will interchange these two summation. So I'll take only those factors such that q lies between 1 to n by d. And if I sum over all the factors or the divisors of n, then these two summations are same.
mm, mm, mm. So yeah. That's okay. But actually, here we have the equation k qd in the final paradox is right.
Yes.
Mu of d equal to mu of k divided to q
Right.
is right because the summation is q,
Yes,
but
yes, guys.
in the formula we don't have q.
Yes, yes, that is fine. But that is the thing we'll use. So summation is over q. That is fine. So since next step we'll use that. So since here there is no q, I
Mm,
can send this one inside the summation. So that is the next step. So for here I can write it as summation over d divides n mu of d times summation q equals to 1 to n by d. This will become 1. So this is my summation. Okay, so this is the double summation. So this is, so here there is a bracket, so I'm just interchanging the bracket.
Yeah, yeah,
So
that is, and we almost prove us.
yes, so
In,
here
yeah,
d divides n mu of d, and how many terms are
yeah,
there in the summation? N by d. So
yeah,
q equals to 1 to n by d, so it is times n by d. So that is what we wanted to show.
yeah. The final two lines is okay, but the third line, at the first line here, at the
Yes,
we substitute q
yes,
q equal to 1 from n over d equal 1 to n over d q equal 1 to over k
right.
k k equal to 1 to n. uh, so we shift the over a the divide d,
Yes,
but
so here
how we
yes, let
can
us,
remove k here.
yes, tell again.
K equal to 1 to n.
Right.
So d plus n, d plus k.
Yes, yes, so d divides n and d divides k. Yes.
Mm. But we remove k here.
Yes, yes. So that is what we are doing here, right? So for any fixed divisor of n, what we are doing is the sum is over all those k for which they are a multiple of d, right? So that's why we are removing that k from there.
We fit divide d of n must sum over on k.
Okay, let us see an example. I think that will be easier, right?
Mm.
So suppose your n is 6, right? So
Mm.
if n or 6, then what is? Let us see what happens to this summation, right? So let us see an example that will be easier to understand. So suppose n equals to 6, then what is my this summation, right? Okay, so if n equals to 6, then you have here this is 6 and here this is 6, right? So from here what you have, k equals to 1 to n, right? So suppose k equals to 1, right?
Mm.
Then what will happen? So the first term is, yes, for k equals to 1, I have d divides 6, d divides 1 and mu of d, right? And then what I have, d divides 6, d divides 2, mu of d, like that I have, right?
Mm.
So this is k equals to 1, the k equals to 2. Similarly, I will have to go up to 6, right? So similarly, the next term will be d divides 6, d divides 3, mu of d, and so on up to the last term will be d divides 6, and this one also d divides 6 because k is 6 here, mu of d. So now let us see what is happening. So if d divides 1 and d divides 6, so only option is d equals to 1, right? right?
1.
Yes.
Ah,
So from the first term, I will only get mu of 1. Right.
ah,
From the second term, d divides 2 and d divides 6. So here it's 1 and 2. Right.
ah.
So this is 1 and 2. Right. So
Yeah,
it's
yeah.
mu of 1 plus mu of 2. Right. So then d divides, if d divides 3, then how many terms are there? Hmm. So d can be 1, 2, and 3, right? In this case, in the third term, this will be the three terms, right? Because d can be either 1, 2 will be not there, sorry, 3, 1 and 3, right?
Mm,
Because d divides 3 and d divides 6. So only possible is 1 and 3, right?
mm,
Or what about d divides 4? So d divides 4 and d divides 6. So it is only 1 and 2, right?
mm,
The fourth term will be 1 and 2.
mm,
Okay, the fifth term is d divides 6, d divides 5 and d divides 6. So only is 1. So fifth term is 1. And sixth term is 1, 2, and 3, right?
mm.
Mu 2, 3, and 6 also. So the up to this part is correct. Is this correct?
Mm.
Up to this part you understood, right? So this is k equals to 1. This term is k equals to 2. This term is k equals to 3. This is k equals to 4. K equals to 5. And this is k equals to 6. So these are the 6 terms of the summation, right?
Mm, mm,
Okay. Now let us see what is happening to the other part. So the other part is this thing. So d divides n. Okay. So here is d divides n and then summation. So here n is 6. So we'll replace by 6. So n is 6. Here also n is 6. So then what will be the terms of the summation? Tell me.
mm.
So d divides 6 means what are the divisors of 6? 1, 2, 3, and 6, right? So here the terms will be summation q equals to 1 to 6 by 1 when d is equals to 1. Mu of this is 1, right?
Mm, mm,
Then plus q equals to 1 to 6 divided by 2. Mu of 2. D is 2. Then summation q equals to 1 to 6 divided by 3. Mu of 3. And final the term will be q equals to 1 to 6 by 6 mu of 6. So this is actually counting how many mu of 1s are there. So here you can see there is 1, 2, 3, 4, 5, 6. And here also you can see that is 6. So this is also you can see that it is 6 times mu of 1. Next is mu of 2 is counting. So here it is 1 time, 2 time, and 3 times. So 6 by 2 is 3. So that's why it is 3 times of mu of 2. So similarly, you can see 2 times of mu of 3 is coming, and mu of 6 is only 1 time. So that is here also you can see it is 1 time. So we are counting the same thing, but in a two different ways. First, we are counting when summation over k, and next we are counting over when d divides 6. Both are giving the same result.
mm, 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 mm. Can I see previous
Yes,
by
yes.
submission? The end here. The end is not related to the first submission.
Yes, yes, it is related, right?
Okay.
Because here we have also d divides n.
Uh, uh, that's that is not. We have two submission,
Right,
but
right. We have
the first submission run from k.
right.
So only the divisor k.
Yes,
Uh,
yes.
uh, uh,
So the thing is, if I have k in the both summation, I am not able to make it right. So I am making it clear of k. I am replacing k by q9 q, so that I can do the summation, because since k is in both of the summation, I am not able to do the summation. So if I interchange the sum, then I can make it free of k and replace it by a new variable q, so that I can do the rest of the steps. So that is the argument.
mm. Q equal to 1, Q equal to 2, 3, 4, 5, 6. Mm, mm. K and K. Uh, yeah, yeah. Yeah, yeah.
Okay. So now I think it is fine, right? The example is you understood, right?
Mm, it's okay.
Right. So what is the formula what that we got is phi of n and mu of d. So we can relate using this formula, right? So this is useful. Okay. So let us see the next one. So it is a product formula for phi of n. So we'll give another formula. So we'll give another formula for phi of n. So that is in terms of the prime divisors. Let us see the statement. So the statement of the theorem is like this. So for any integer n greater than equals to 1, we have this phi of n is equals to n times the this pi notation, you know, right? Product. So p divides n, 1 minus 1 by p. So
Mm,
this notation, you know, right?
mm,
Right. So for example, let us see what we are doing. So suppose I want to find phi of 6. So it will be, what are the prime divisors of 6? So it is 2 and 3, right?
mm,
So it will be 1 minus 1 by 2 times 1 minus 1 by 3. Anything else?
Product formula of phi n. Uh, product formula of phi n.
Right.
In pi, yeah, pi. Pi is multiply 1 over p. Ah,
Right.
yeah, yeah, yeah. It's okay.
So yes, if you check this, so this is nothing but half, and this is 2 by 3, right?
Mm.
So this is 2. So and phi of 6 is 2, right? That we know. So let us. So this identity is you understood, right? What we are saying,
Got it, got it.
right? So let us prove this one.
Phi, phi, phi is phi is a number relative prime. Mm.
Yes, yes. Number of relative times
So
that
since
is less
we
than.
have 2 and 3, it's
Right.
not since we have 3. No. Six we have 1 and 6 is right.
No, no. The relatively prime number that is less than that number, right? So 2 and 3 only, right?
2 and 3, 2 GCD of 2 and 6 is not 1, is right.
Yes, yes. No, two numbers is your two and three are the prime numbers, right? So here in the product there are two numbers, 2 and 3, right?
2 and 3.
Right.
I
So what?
want to see the 5 5 again.
Oh,
5
five,
and 6.
five. Yes, 5 of 6. The prime numbers that are 1 and 5.
Mu mu is that's E5. Ah, that's E5. B power alpha 1 on alpha equal to 1 is right.
No, no, that is mu.
That's email. That's email. Mu is 1, 0, and minus 1 is right.
Yes, yes, that is mu.
Mu. And phi is phi is relative prime.
Yes, relatively prime. The numbers less than that. So here is 1 and 5.
1 and 1 and 5. Yeah, 1 and 5. Okay.
Right,
1 and
one and
5. 1 and 5. Yeah, 1 and 5. Yeah, it's okay. 1 and 5.
right. So let us see the proof. Okay. So if n equals to 1, then we have nothing to show, right? Because no prime divides n. So n equals to 1, so the result is true, right? So that is fine. So now we'll take only the things where n is strictly greater than 1. So if n is strictly greater than 1, and let p1, p2 up to pr be the distinct prime factors. Distinct prime divisors of n. Right. So then if I take the right hand side product, let us see what happens. So product p divides n. So this is nothing but product I equals to 1 to r 1 minus 1 by pi, right? Because these are the prime factors of n, distinct prime factors of n, right? Fine.
Mm. Mm.
Okay. So now if I expand this, if I multiply all the terms and write it, so then it will look like this thing. So it will be 1 minus summation 1 by pi
Mm.
plus summation 1 by pi pj, then minus summation 1 by pi pj pk, and so on up to the last term will be minus 1 to the power r p1 p2 all the way up to pr. So this is if I expand this multiplication, this will come, right?
1 by 1 by A by Z by K. Wait, we have 1. Yeah, that was the 1. So
Yes.
we have 1. Yeah.
Right.
Yeah.
So we'll have alternate plus and minus, right?
Ah. Hmm.
Right. So let us understand what are these terms contributing. So the thing is, so on the right hand side, what we have is so suppose if I take this term summation of 1 by pi pj and pk. So if I take this term, right? So here we consider all possible products this thing. So we consider all possible products. Um, Pi, Pj, Pk of distinct prime factors of n, taken 3 at a time, right? So
Mm.
here summation has all these terms, right?
Mm.
Okay, so here we have, the d is a divisor of n, right? So this summation part is clear, right? So how many times we are taking? So this summation has all the things. So we are taking three distinct prime factors, taking 3 at a time, right?
Three times. Distinct factor. Taking it three times.
Right.
Mm. We consider unreversible product of PCC 16 gram factor on a tracking three times. We
Right.
consider one possible product P I J K of distinct gram,
Right.
distinct gram factor on K. Yeah. Mm,
So what we can do is, so this is nothing but each of them is a divisor of n, right? So if I so
mm,
each term is a divisor of it, right? So that is this py, pj, pk. So that divides n, right? Because these are the prime factors of n, right? So each term, so this is of the form plus minus 1 by d, where d is the divisor of n. So it is either positive or negative according to the sign what is there. So each number is reciprocal of some divisor, right?
mm, mm,
So each number in the summation on the right hand side. So this is nothing
mm,
but 1 by d for some divisor of n, and it is either plus or minus. That is depend upon the sign, right?
mm.
Fine,
Yeah, yeah. Mm,
right? But sign actually we can do it, right? So I know what is, so when mu d. So this is nothing but minus 1 to the power k, right? Where k is a number of prime factors in d, right? Right. So if d is suppose pi, pj, and pk, then mu d will be minus 1. Sorry, this is not the same k, but here some star. So this star is number of prime factors. So it is nothing but 1 minus 1 cube. So it is minus 1, right? So this minus 1 every term, whether it is 1 or plus this thing. So this thing is nothing but mu of this coefficient, right? Because we can take it inside, right? You are getting
Yeah,
what
yeah.
I'm saying?
Yeah, 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 yeah. I'm using. Yeah. Okay.
Yes. So this thing, so I can take in the negative sign as a mu term, right?
Hmm.
And also you can see that there is no repeated term here, right? So if mu p square or any higher power of p is not here, right? So that implies that we can also take it consideration since mu of that divisor will be 0,
Hmm.
right?
Yeah. Hmm.
Right. So what is okay, let me copy this one.
Hmm.
So what I can do here. So this thing is nothing but this is 1 plus summation. This is mu of pi because that is already minus 1. This is pi. This is plus summation mu of pi pj. That is minus 1 there, so that is become plus 1 pi pj. Then it is again summation mu of pi pj pk. So everything becomes plus, right? And so on. The last term will be mu of this product p1 up to pr, p1 p2 up to pr, right?
Hmm. Hmm. Yeah.
Right. So from here directly I can say, so this is nothing but summation over d divided n mu of d divided by d, because all of them are divisors of, so all these quantities are divisors of n, that will already come into this summation. But if some more divisors are there, so then at least the number is not square free. Square free means it has some prime power that is bigger than equals to 2, right? So in that case, the mu will be 0. So that will be not contributing in summation. So the reason is, let me write down. So since mu of d is 0, if d is divisible by b square of n, right? So using this thing, so any other divisors of n which has more prime factors, means each prime factor is coming more than once, then it will become 0. So I can write that this whole summation I can combine a single summation. Okay.
Hmm. Yeah, yeah.
Okay. So what I got is till now what I have done is, so pi of p divided 1 minus 1 by p. So this is nothing but summation over d divides n mu of d divided d. So this I got. But now the previous theorem what I got is, so now I'll use the previous theorem. So here you can see if I copy this one. So this was the previous theorem. So now if you use it here, okay. So this is nothing but n is not in the summation. I can take n outside. So d divides n mu of d by d. This is same as this quantity, right?
Hmm. Hmm. Hmm.
Yeah. So now, so what I do is both sides of this equation I multiply by n. So if I multiply both sides by n, so what I have n times p divides n, 1 minus 1 by p, that is nothing but n times summation d divides n mu d by d. But this is nothing but phi of n. So this comes from here. Okay. But this is what we wanted to show, right? So I wanted to show that phi of n is nothing but this quantity.
Yeah. I see a little bit. Yeah.
Yes.
Yeah. Yeah. Mm. 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 Equal to mu pi. Pi z. Uh, number of factor. Yeah. Number of factor. Uh, mm. Mm. Mm.
Okay.
A little bit scroll down from
Yes.
the yeah, here it's okay, the right hand side. bi bi is bi is a divisor, on divisor we have r divisor of n, is right.
Yes.
We have r divisor of n, bi to be r, uh, b1 b2 bi distinct prime
Distinct prime divisors of n. Yes.
distinct prime divisor. That means in case of sheet we have
2
two,
and
three,
3. Yes.
not sheet. Yeah.
Mm.
Okay. In case of 20, we have only
2 and 5.
two, five. Two,
Yes.
five. Uh, the right hand side bi is, say we consider unbossable product of
Right.
in prime factor on n. Second it 3 times.
Hmm.
Mm. Atomy divisor of n, so on product is divisor of n. Oh, it's
Right.
yeah, that's right, because it's a sub multi
Yes.
product
Yes.
of 1 to r. Yeah.
Right.
Mm. And the form plus minus d,
Yes.
where d is divisor of n.
Yes. But we can take the minus sign and the plus sign inside because that is nothing but mu of the denominator.
Uh, uh, yeah. Mm. Plus of minus d, where is plus of minus d?
No, no, I'm saying that in this summation, we have some alternate plus and minus, right? This alternate plus and minus. I can take it inside because this is nothing but mu of the denominator. Because the number of prime factor is either odd or even. That will depend upon whether it is plus or minus, right?
Mm, mm, mm,
Yes.
mm,
So from that, I can directly say that this is the summation because if any higher prime factors are there, this is automatically becomes zero. So that will
mm,
not contribute into the summation.
mm, mm. Yeah.
So from here I get this one and I multiply both side by n
Mm,
because from the previous theorem I know that phi of n is nothing but this quantity.
mm, mm. Yeah, yeah. Mm. Yeah.
Okay.
Mm.
So I think so. This was our theorem. So this is product formula for phi of n in terms of finite vectors. So today we'll stop here then.
Yeah, yeah.